So today, by the way, welcome back. So today we are going to do probably the most important theorem in optimal transport during the last 30 years, in my opinion, which is Brenier theorem. So we will prove that theorem. I know that Professor Sumik already gave some sketch of the proof, but today it is going to be a little bit more detailed. And then there is an extension of Brenier theorem called Gango-Mechan theorem, and we will elucidate, and then you will learn how to prove it. Okay, and then on Wednesday, we will connect Brenier theorem to partial differential equations called the Monge equation, and then you will see some exciting applications of that. Okay, so James, did I start a recording?
Yes.
That is the red button, right?
Okay, good. Okay.
And you also mentioned that you start recording.
Okay. Anyways, it's your job to monitor that, okay? Okay, what is Brenier theorem? So we are considering Rn as our underlying space. We have two sets, that's X and Y. For technicality, we just assume that X and Y are the closures of some bounded open set. Here, the boundedness is important for us. There's some kind of compact set. And then the cos function is the distance square. So we are using the Euclidean distance, so distance squared. And source measure mu and target measure nu are probability measures. I mean, they have the same total mass, that's the point. And then we assume that the source measure mu is absolutely continuous with respect to the Lebesgue measure. Okay, you will see why this assumption is relevant for us. Okay, and then we learned that in this setting where the cos function is like continuous and the domains are compact, we know from the very like soft analysis that there exists optimal solution. Okay, optimal transport plane pi as a measure on the product space exists. You can prove it by very soft analysis using weak star convergence. But uniqueness of such a solution, I mean, does not hold in general. You can easily find many counterexamples. But in this case, in particular, here important thing is mu is absolutely continuous, and the cost function is of some special form like this, but it can be more general. But at least this cost function has some special property. And there, the optimal solution is unique. Okay? The uniqueness is very good, but there are more exciting things about this Brenier theorem. Namely, the optimal transport plane is given by a mapping. So transport plane is just a measure, right? If you remember, you have to, we have source domain and target domain. You have mu, source measure, and target measure, and then transport plane is like a measure on the product space, like some measure like this, okay? But here this theorem says the transport plane is not just a measure on the product space, but you can represent it as a mapping. Namely, for each almost mu almost every x, you can find the corresponding target point y as a mapping. Okay. So what's the difference? Transport planes, given x, you may split the mass into several locations. Okay, like you transport, let's say, I don't know, a pile of dot here in this room to another room, then you may split the mass of the pile of dot into several, I mean, many paths, and then you can spread that path over the other room, right? But mapping is like this pile of sorry, maybe for mapping means each, it's like, let's say, you transport people in this room to another room. You don't want to split a person, right? Am I right? Right? You don't want to. So a person goes to one location in another uh, room, right? That's like mapping. Okay. Okay. And then not only that, I mean, that's not the end of the Brenius theorem. Brenius theorem says such a mapping transporting the source measure mu to the target measure nu is of very special form. Namely, it is the gradient of a function, and the function is also a very special function. It's a convex function. Okay? So all these things together are in Brenius theorem. Okay? And such a function can be uniquely determined up to additive constant. So basically, this mapping is unique because optimal transport plan is unique. Okay, question. Any question from the Zoom? Okay. In the literature, such a solution coming from Brenius theorem is called sometimes Brenius solution, but more often is called Monge solution, because Monge considered the problem of finding an optimal mapping, and Brenius solution gives a solution to Monge's problem. And the solution, the optimal transport plan we discussed before are often called is often called Kantorovich solution. Okay? Because Kantorovich is the person who considered this transport plan problem. All right. Okay, then how do we understand and prove this Brenius theorem? Okay, so to understand this, we can just review how we got the transport plan and the associated duality. So the primal problem was to find a transport plan which has marginalized mu and nu, minimizing the transport cost. And there is a dual problem. Here you have, for each of these dual constraints, you have corresponding so-called dual potentials. Okay, you can assume them to be continuous. And then this cost function will give us this condition that then dual potential phi x plus psi y has to be bigger than or equal to negative cxy for xy in xy. Okay. Then we proved three important theorems for duality, namely no duality gap. This infimum value is the same as this supremum value. So dual problem is a maximization problem, maximizing this this functional, which is a linear functional on phi and psi. Of course, we are assuming that x and y are compact metric spaces and C is a continuous function and so on. Okay. And then there's dual attainment, means these dual potentials have optimizers. So you have optimal phi and psi realizing this supremum value. Okay. So dual problem has an optimal solution, phi bar and psi bar. And then these dual attainment actually, if you remember the proof, came by replacing this general dual potentials with C convex functions. You remember that? Yeah, we took some C transform and make them C convex functions. After C transforms, the dual functional becomes larger, so we can just restrict ourselves to C convex functions for this maximization problem. Okay, and then in the end, what we have is that okay, so these dual optimal solutions are C convex functions. They are C transform of some functions, but the other functions are just the other function in the pair. So phi bar is a C transform of, sorry, psi bar is a C transform of phi bar, and phi bar is a C transform of psi bar. So they have this pair, phi bar and psi bar have this mutual property, which is important for us, okay? And the third important theorem is so-called complementary slackness. It says that the optimal transport plane, pi bar, is supported only where this dual condition, dual constraint is saturated. Okay, so dual constraint is only this inequality, but complementary slackness says optimal transport plane happens is supported only where this dual condition is saturated. That's this thing here. Okay, for the optimal dual solutions. Okay, am I making sense here? I'm just reviewing previous lectures here. Okay, all right. So if you combine these two, then what we have is phi bar x plus phi bar c y is, I mean, let me just use, okay, plus cxy equals 0. Okay. Or of course you can just write it this way. So phi psi bar c tilde x plus psi bar y plus cxy equal to 0. Of course, these two are the same condition, same statement, I mean equivalent. But this thing that the optimal transport plane is supported where this condition for the dual optimal solution and its C transform is saturated. Okay, so that's what we want to investigate. Okay, below to understand how we get Brennan's theorem. Okay, so I think you learned this notion of C subdifferential. Am I right? Anyways, we just define it. Just it can be a review for you. So given a C convex function, okay, so C convex function is given by C transform of some other function. Okay, you can define the C subdifferential first. Okay, so C subdifferential, you can define it as a set of pairs x and y, the product space, where phi x plus phi c y is equal to negative c x y. So this is exactly the set. This is exactly the set. I mean, here for when phi was phi bar, I mean this is exactly the set here. Okay. So C subdifferential is nothing but the pair of points where these conditions. So in general, you have inequality here, right? So C Legendre transform is always bigger than or equal to, remember, C Legendre transform is always bigger than, which is a supremum of minus CXY minus phi x for all x. So this is always bigger than or equal to any for any xy, right? So C subdifferential is exactly the set of x and y where you have equation. Okay, and C is C subdifferential. So C subdifferential is a set in the product space, some set of points. Okay. And then the C subdifferential of phi at a particular point x is you just pick x here, okay? And then you pick the corresponding y's in this set where set of C subdifferential of phi. So this is nothing but the set of y where this equation is satisfied. Any question about this definition? Yes.
Why do we require the phi to be compact?
That's a good question, and the answer is you don't need it. Okay.
So it appears just for conventional reason.
Well, if phi is not C convex, then C subdifferential can be empty, an empty set or something like that.
So we want to ensure the emptiness of the theta equation.
Or more practically speaking, I mean, you will consider C subdifferential only where phi is C convex function in this context of optimal transport.
Okay.
But of course, you can consider this in more general case. Yeah. Other question? Yeah, so the question was, what is the relation between C subdifferential? Why do we call it C subdifferential? It's not C differential, sorry, C subdifferential. And what is its relation to the usual subdifferential? So we will consider that in a moment. Other question? Okay, so this is for phi on x, but I mean, for psi on y, you can also consider C subdifferential. Okay, just by the same principle, you first consider this set where phi, the set where, so C subdifferential of psi. Let me use tilde because when we use y as our domain, we use tilde, is the set of xy where psi C tilde x plus psi y, sorry, is equal to negative C xy. So you always have this inequality, but the C subdifferential is exactly the set of points where you have equation there. Okay, and then, so this is like you have x and y for each given y. I mean, before you consider this, you have this a set, the C subdifferential of psi, right? And then there for each y, you consider the set of x belonging to this set. That is exactly this definition. So C subdifferential for each x is a set of, for each x is C subdifferential is a set of points, okay, in y, if you consider C subdifferential at x, or it is set of points in x if you consider C subdifferential at y. Okay. Actually, a very easy exercise or important exercise you want to do is the following. If phi is a C transform of psi and psi is C transform of phi, like in our optimal dual solutions, okay? Then the C subdifferential of phi, which is set in the product space, and the C subdifferential of psi, which is a set in the product space, they are equal. This is extremely easy to see. Okay, maybe let's do it now. Okay, why is it true? the question is why this is true. Oh, yes. Yes. If you take C transform twice, then you recover the original. Okay, then. This is extremely easy to do. In fact, okay. Yeah, it's exactly, yeah. So maybe you can just say by definition, but if I just ask more, okay, by definition, how?
By psi of c order and by c is psi.
Right. So
So
here,
these two are the same.
yeah, exactly. So this, look at this. This is exactly this in this case, and this is exactly this. So these two equations are exactly the same equation. So the corresponding set should be the same. Okay. So it's kind of like symmetry. I mean, you view the same set here from the point of view x, or here from the point of view of y. Okay. But the corresponding functions are not the same. They are related. They are C transform of each other. Okay. You can see the same feature in a more interesting way later. Okay. Yes.
When we say when we talk about C complex functions, do we always talk about a pair of
Yeah. So when you consider C convex function, you can always consider is the function whose C transform gives that current C convex function. So you can always consider pair. You don't have to, but there is always a pair.
So most of the time we talk about the two functions together.
Yeah, that's maybe. So most of the time, you want to consider those two functions together. You want to, okay, to understand the feature in a better way. Okay, good point. Okay, now what's the relation between subdifferential and C subdifferential? So let's just consider, I mean, the short answer is that when we have this cost function, the dot product cost function, then there the corresponding C subdifferential is exactly the same as subdifferential. Okay. So for example, for convex function, you can consider the subdifferential. You learn that the subdifferential is like this thing here, namely, the geometric meaning is like you have Rn, you have R here, you have some function, let's say in this case U, okay. A convex function like this, okay, and then at each point x, you consider those supporting hyperplanes, okay. Supporting hyperplane will have some equation like, I don't know, x dot y, maybe y dot x, uh, minus something, right? Here, some constant plus some constant is a function of x, okay? So those, the slopes y, the slope of the supporting hyperplane belongs to the subdifferential. Okay, the subdifferential is nothing but you consider the supporting hyperplanes of the convex function u at a point. There can be many supporting hyperplanes, right? In particular, when the function is not differentiable. right? The function may look like this. Then you may have some other supporting hyperplane, like I don't know, like this, or something like that. Yeah. But you just collect all those slopes of these supporting hyperplanes, then the set of those slopes give the subdifferential. Okay, that's the usual definition of subdifferential. But if you think about it, such set of y is exactly the same as those y's that saturate this in this the inequality, the Young's inequality, right? Young's inequality is exactly this. And then those y that saturate this Young's inequality is exactly the same y giving the slopes of supporting hyperplane. Okay? Okay, why are they the same? So that is your exercise. And do you think you can do this exercise yourself? Okay, so people are nodding, so let me skip it. Just the idea is just because the convex function is Legendre transform of its Legendre transform. So you really need to, you just need to remember the meaning of Legendre transform. The convex function is Legendre transform of this U star, means when you consider these supporting hyperplanes, the supporting hyperplanes are given as x2, x star y minus u star y. So this note is related to the statement that your function, your convex function is a Legendre transform of its Legendre transform. So here, for this constant part here, you have this Legendre transform of the original function. Okay. All right. And there are many like examples you can compute the subdifferential. And when you compute the subdifferential, of course, intuitively, it's much easier to use this definition that subdifferential are nothing but the slopes of supporting hyperplanes. Then you can easily compute the subdifferentials of these functions. And you also can easily prove, I mean, using either of these definitions, that subdifferential of a convex function at a point is a convex set itself. Okay, and here comes an interesting part. So, right. So remember, if phi is a seed transform of psi and psi is a seed transform of phi, then their C subdifferentials are equal, the same set in the product space. Remember, I'm talking about this property. Yeah. Okay. So if you apply this to Legendre transform, phi is a Legendre transform of psi, and psi is Legendre transform of phi, then their subdifferential should be equal. Okay. So that is this statement. The subdifferential of u for each x you collect those y's. It's the same as the subdifferential of u star for each y you collect those x. Yeah, the equal set. Okay. So here, this means you have the same set here. You can view this set from the point of view x. So that's why you consider this x first and y. But you can consider the same set from the point of view y. Let me write it this y. Okay. Then you have u star subdifferential, and each y you have x. Okay. So these two sets are, I mean, they're equal set in terms of the pairing x, y. But if you regard this x, y to be just Rn, okay, then these two sets are, if you consider this expression, they are inverse to each other, right? X, y now becomes y, x. So it's the inverse relation. So this suggests that the subdifferential of u is the inverse of the subdifferential of u star. So if you remember, when u and u star are differentiable, the subdifferential of u is nothing but the gradient, right? So this is if u is differentiable. Then subdifferential is nothing but the gradient. And gradient can be understood as a mapping from x to gradient of u. Now, then this subdifferential, which is just gradient of u, should be inverse to the subdifferential of u star, the gradient of u star, when u and u star are differentiable. So that is this relation that they are inverse to each other. So repeating again, the gradient, okay, suppose u and u star, the Legendre transform and the original convex function are differentiable, then the gradient of u is the inverse of gradient of its Legendre transform, vice versa. The gradient of the Legendre transform of a convex function is the inverse function of, is the inverse of gradient of, okay? So in optimal transfer, how can you apply that? So when you find an optimal transfer plan, optimal transfer mapping from x to y, let's say using Bragnier theorem, then sometimes you may want to find the inverse mapping. And the inverse mapping is, to compute the inverse mapping, you can compute the Legendre transform of your potential function u, and then you can take the gradient. Then it's the inverse. Okay. Okay, any question about this page? Okay.
The last one holds up to almost everywhere, right? It should.
Yeah, so when it's differentiable, you just have them everywhere. But when they are only ellipses, then yeah, these relations are almost everywhere.
Okay.
Okay. So subdifferential is where, C subdifferential is nothing but usual subdifferential if the cost function is this dot product cost function. Okay. Okay, in Bragnier theorem, we are considering this scared distance. Okay, so what's then the relation between the C subdifferential of the scared distance cost function and the usual subdifferential? Okay. So here, this, if you look at this distance squared, which is, it is x square and then y square and minus x dot y. So somehow this function is related to this dot product cost function. Okay. Okay, then what is the precise relation between the C subdifferential of C convex function of this distance square cos function and the usual subdifferential of a convex function? Okay, first of all, given a C convex function, so C convex functions are given in this way: supremum of is three-Legendre transform of this, right? So this is a characterization of a C convex function. Okay. Okay, then when C is this squared, so this is minus x squared over 2 minus y squared over 2 plus x dot y and minus y cy, right? So if you rearrange things, then what you get is no, right. First of all, here this x square is independent of this y, so you can be outside of the supremum. And the remaining ones are x dot y minus phi cy plus y square over 2, like this. Okay. So what does this suggest? It suggests the following equation: phi plus x square over 2 is supremum of y of x dot y minus phi c y plus y square over 2. Okay. And what can you say once we see this equation? Okay, remember, we are exploring the relation between the C subdifferential and subdifferential when C is this x minus y square function, cos function. Don't be shy. James, what can you say? Yes, so you should have told it earlier. Don't be shy. This is Legendre transform what function? This function, right? So what we have is this function, if you just define as u, which is just there, this is Legendre transform of this function. Okay. So Legendre transform. So it's a convex function. Obvious, right? And second, if you consider this function again, okay, so this, let me leave it as an exercise. Then this function, in fact, this function is a Legendre transform of this function, meaning this function is also convex. Okay, this function is convex. So its Legendre transform is u. So its the Legendre transform of u is again back this function. Okay, so that is what this second line says. And important for us is this relation because here the C subdifferential of phi is exactly the same as the subdifferential of u when we just add to phi this x squared over 2. Okay. Is this clear? And of course, this is your exercise, but you think you can handle it? Okay. You can just look at the definition here. What is the so to understand that you can just look at this phi x plus phi c y is equal to negative cxy. Okay. And this for that you have to consider this let's say ux plus u star y equal to x dot y. So you just compare those x and y satisfying these two equations. And the claim is they are exactly the same. Okay. So that is the relation. So C Legendre transform of this distance squared function over C convex function is the same as just the usual Legendre transform of this function u, which is nothing but the original C convex function phi plus this x squared over 2, which is again a convex function. Okay. So we kind of turn a C convex function into a convex function in this way. And the C transform, C subdifferential as the ordinary subdifferential. Okay. And when the function u is ellipsis, we know that the function is differentiable almost everywhere by Rademacher theorem, and the subdifferential in that case is almost everywhere the same as the gradient of that function u. Okay, so this is a key relation for us. Okay, any question about this? Okay, now we are okay, so we already did this exercise and why we have convexity for such u. Okay, then using this observation, we can prove Bragner's theorem. Okay, so remember Bragner's theorem just tells that the optimal transport plan is given by a transport mapping, optimal mapping, which is the gradient of a convex function. I mean, almost every sense. How do you get that? Okay, let's prove it. And here we have assumption. Of course, the C is this distance square function, and the mu is absolutely continuous, and x and y are bounded. Okay, so we are going to prove it now. Okay. Okay, where should we start to prove Bragner's theorem? James? Where should we start? Start. What should be our starting point for proving Bragner's theorem? Yeah, so where can we get the C convex function then? No, before that. So where do you get such C convex functions? Yes, exactly. So we can start with the dual problem, and we can find an optimal solution there. I mean, we have the dual attainment. So we have this dual optimal solutions, which are C convex functions. Okay. Right? And complementary slackness says the primal solution, optimal transport plane pi bar, is supported only where this dual constraint is saturated for the dual optimal solutions. Okay. Okay. Right. Okay. And or minor, I mean, but important thing is that our domains are bounded. So source domain and target domains are bounded. And if you okay, maybe before that, let's just remember. Okay, then for the C convex function phi bar, you can consider, you can just define a new function u, which is just by adding this x squared over 2 there. Okay, so phi bar was C convex. C convex with C just x minus y squared over 2, right? So if you add this function to such C convex function, then the resulting function is convex, right? We just did in the previous slide. Okay, then for this convex function, we know that there and phi, yes, we already saw phi bar. So phi, the C subdifferential of phi is the same as subdifferential of u, right? We just did it in the last slide. I mean, exercise, but okay. Now, the subdifferential of u, okay, is nothing but the collection of the slopes of the supporting hyperplanes, okay, right? The slopes are y, and those y are the points in, okay, so C x, so set of y, right? That y belongs to the C subdifferential phi, right? And then C subdifferential phi, I mean, if you consider, remember where this x and y are coming from, okay, x belongs to x and y belongs to y, and x and y are sets in Rn bounded open, okay? So those y's, the slopes for the convex function u belongs to a bounded set. This should be a subset of y, which is bounded and open. So this subdifferential is bounded, okay? And this boundedness is uniform because you have the same capital Y for every x, okay? So it says the slopes are bounded, uniformly bounded. The functions, these functions, so this function u at each different points have different slopes of supporting hyperplanes, but these slopes are all uniformly bounded, okay? That means what? Such a function should be, that's exactly the definition of ellipticness, okay? So that's here. So this ellipticness comes from, especially from boundedness of y, okay? So you have ellipsis function. Okay, now you have your optimal transport plane pi bar is supported on the subdifferential of the convex function u, but the convex function u, it has supporting hyperplanes whose slopes are all uniformly bounded. That means the function u is ellipsis. Okay. That means the function u is differentiable almost everywhere. Okay, because of Rademacher's theorem. That means the subdifferential of u, actually is here. The subdifferential of u for almost every x is the same as the gradient because of Lipschitzness. Okay. Fine. So far what we did is just we had this C convex function and C subdifferential where the optimal transfer plane pi bar is supported. We just translate the C subdifferential of C convex function into the subdifferential of a usual convex function, but this convex function is Lipschitz because all the slopes are bounded because the capital Y, the target domain, is a bounded set. Okay, now using this derivative gradient of u, we can just define a mapping. So Tx is the gradient of u for almost every x. Okay, we just define a mapping, define almost every x. Okay. So just translate back to the subdifferential, then the subdifferential of u is almost everywhere the same as this mapping T. Okay. But now it was almost Lebesgue almost everywhere. But mu is absolutely continuous. Means if the set is measure zero with respect to Lebesgue, it is also that means if anything is Lebesgue almost everywhere defined, then the same thing can be defined mu almost everywhere. Okay. So now we have this relation mu almost for mu almost every where x. Okay. Okay, so far so good. Question? So we have in ID we have some set x, some set y, and we have some subdifferential of u, which is the same as the subdifferential of phi bar. Okay, and then for each almost every, let's say x, mu almost every x, we now define is t is tx as our y. Okay. And now optimal transfer plane pi bar. I mean, I use this the word supported, but more appropriate wording is so pi bar is concentrated in the set. Right. So when you see this equation, it means you can say pi bar is concentrated in the set, this set, subdifferential of u. Okay. So that means your pi bar, the pi bar is some measure here. It doesn't have any mass outside this set. So having mass somewhere here is not allowed. The mass of pi bar is only inside the set. Okay. I mean, this is equal to 1 means, but 1 is the full measure of pi, right? So then this means, i.e., pi bar outside of the subdifferential is 0. Okay. So it has mass only inside the subdifferential of u. Okay. So this relation here for each mu almost every x, you have y tx. I mean, this differential is exactly this mapping point tx, whose mu almost everywhere, but because this pi bar has marginal mu, okay, your pi bar or measure here has marginal the same as mu. It means such relation for mu almost every is actually the same relation for this x and y for pi almost every x and y. So let me give you just a few moments to understand this. Okay, and this relation that you have this mapping relation between x and y in pi bar with this mapping t is exactly the same relation that the mapping t pushes forth this mu marginal of pi bar to the other marginal of pi bar. Okay, so this relation is exactly the same as this because pi bar is in has the marginalized mu and okay, so just take some time to understand this statement. I'm not going to do the details here. Okay, you have to understand this too. Okay. So we get the optimal mapping T pushing forward mu to nu given as the group of convex function. Okay. All right. Any questions so far? James, any question? No? Okay.
Reading the deadline.
All right.
Big tab.
Okay. All right. Okay, then, so that's the proof of this characterization of this optimal transfer plan in Brennan's theorem. And then uniqueness. Uniqueness is kind of easy to see that you suppose you have two transfer plans, pi bar and pi bar prime that are optimal. Then you have the corresponding potential functions, let's say u and u prime, okay? I mean, the dual problem may not have optimal solution either, right? But the thing is, for any dual optimal solution, for any u or u prime, you have this relation, the complementary slackness, right? Okay. So for any pi bar and for any u, you have this relation from complementary slackness. So you can apply this to pi bar prime and u prime, and with these different combinations. Okay, now we learned that this means, at least I left you to think about, this is exactly the same as having this relation. Oh, sorry. Having this relation, right? Namely, on one hand, for pi is given by the mapping as the gradient of u. Okay. Also, the same pi, because of this relation, is also the mapping given by the gradient for u prime. Okay. The same for pi prime. Pi prime, which satisfies this relation here. So pi prime can also be given as the gradient of u. Also, because of this, pi prime is given as the gradient of u prime. Okay, so on one hand, you have gradient u here for pi, and the gradient u for pi prime. That means pi and pi prime, pi bar and pi bar prime should be the same. Okay, right? So there's uniqueness. That's why this optimal tensor plan is unique. So this implies this, and implies that, and this implies this, and this implies that. So the optimal transport plane is unique and is given by the gradient of a convex function. And then you may ask, then do you have any uniqueness for those convex functions? James. Right. So between u and u prime, the only thing we have is that their gradients are equal almost everywhere, or mu almost everywhere. Okay. So for example, you can just add any constant to the other, still the gradient is the same. So you have this ambiguity up to additive constant. Okay. So the theorem is just up to additive constant, such function u is unique. Okay. Because the gradient is just unique. All right. Okay. Can be uniquely determined up to an additive constant. Okay. The proof of Grenier theorem. Okay, any question about that? Let me give you some time to think about it. Okay, so for the remaining, let's say 20 minutes, let's consider some more general cases. Okay, so Grenier theorem was the case when the cost function was this just the Euclidean distance squared on the Euclidean space. Okay, but of course you may ask many other questions. Okay, what if the you have different cost function. In particular, what if you consider, like, let's say, not just Euclidean space, but Riemannian manifold or some other metric spaces, or just simply some other cost function even on the Euclidean space. Okay, there can be many maybe useful other types of cost functions. In particular, as you can easily consider the power cost function, right? And others. And then the message is we can generalize Brenner's theorem to more general cost functions. If the cost function satisfies some structural condition. So that's the context of Gangbo-Mechan theorem. It is Gangbo theorem. Okay. Okay, so to do that, let's just review something from one of the previous lectures. Okay, so there we kind of studied some properties of C-convex functions adopting nice properties of the cost function. So if the cost function is, let's say, is uniformly continuous with some modulus of continuity, then the corresponding C-convex function has the same modulus of continuity. Okay, it was an exercise. Also, if the cost function is Lipschitz with some Lipschitz constant k, then the corresponding C-convex function, any C-convex function is Lipschitz with Lipschitz constant k. Okay. And I think we also considered a semi-convex function. Do you remember what semi-convex function was?
And a multiple square, normal square.
Yeah, right. Okay, good. So anyways, we'll just briefly review it, but anyways, the point is that semi-convexity of the cost function will also be translated, will be inherited by any C-convex function. Okay. All right, so it's just simple principle in this exercise that suppose you have some family of functions, okay, and then you take a function as a supremum of that family of functions. So remember, so you have some family of functions, let's say phi alpha with different alpha, okay, and then you just take supremum. Like it. Okay, so that's the situation there. And suppose this supremum has finite values. Okay, now then we have these properties. If each phi alpha is uniformly continuous with the modulus continuity, let's say delta, then the supremum of that family has the same modulus of continuity. If each phi alpha is Lipschitz with Lipschitz constant k, then the supremum of the family has also the same Lipschitz constant k. If phi alpha is semi-convex, okay, what is semi-convexity? A function is semi-convex if you can turn it into a convex function by just adding this quadratic function. Okay, if you add some quadratic function and you can turn that into a convex function, that function is called semi-convex. Okay. So basically, semi-convex functions are nothing but convex functions plus some twice differential functions. That's what semi-convex function is. For example, a function may look like this. So this is a semi-convex function as long as you have some angle of this cusp. Okay, this is semi-convex. Okay, as long as you can find some angle there, because this one is basically sum of this function and and something like, I don't know, something like that. Okay. Okay. So they are semi-convection functions, and then let's just call this K, for this K, just the semi-convexity constant. I don't know whether this is an official name, but let me just use it. Suppose this phi, each phi alpha is semi-convex with this K, the same K for all alpha, then the supremum of their family is also semi-convex with the same constant K. Okay. So you can easily prove these all properties. So if the family has nice properties, then the supremum for their family, given in this way, also enjoys the same nice property. Uniform continuity, ellipsisness, and semi-convexity. Okay, so that's why you have all these properties. That if C have one of these nice properties, then the corresponding C convex function, which is given by the supremum of those functions, again enjoys that nice property. Okay, good. Okay, now you can consider self-differential also for semi-convex functions, because basically semi-convex function is a convex function plus twice differential function, right? So you can basically so if this is phi, and this is, let's say, I don't know, convex function u, and this is, let's say, another function eta. So then subdifferential of phi is basically subdifferential of u plus derivative of eta. Okay, something like this. So basically, semi-convex function can also have subdifferential. So subdifferential, this notion of supporting hyperplane, okay, is originally for convex functions, and you can relax, or you can consider the supporting hyperplane also for semi-convex functions. So without this is the relation between the original function and the supporting hyperplane. So if you convex function, then you have supporting hyperplane, then you have this inequality between the supporting hyperplane and the convex function. But you can relax that relation up to certain small error. Okay. So here you can still have supporting hyperplane. Okay. For such semi-convex functions, right? Maybe more clear example would be something like, I don't know, like that. Right. We do something like, okay. So this is a graph of a semi-convex function, but then you can have supporting hyperplane like this way. So it is not exactly supporting because it goes beyond the function phi, but the error here between the supporting hyperplane and the original function is small. Okay, that's so in that case you can still define the subdifferential, and then it has the same nice properties as the usual subdifferential for the convex functions. Okay. Okay, then the point is, in general, for general C, there is a relation between the subdifferential of your semi-convex function and the C subdifferential of it. Okay, let me repeat. So suppose your phi is a C convex function where C is nice, twice differentiable, and the second derivatives are bounded. Okay, nice. Then first thing is phi is semi-convex. Why? Because phi is given as a supremum of okay. So phi is a C convex function. It's a supremum of some C functions, right? So phi is a sup of minus cxy minus phi cy. So supremum of some functions given by cost function c. So if the cost function is twice differentiable and nice, then with a semi-convex constant, let's say k, then its supremum, the supremum of that family is also semi-convex with semi-convex constant k. Okay, so in that way, your phi, the C convex function is semi-convex, and you can consider subdifferential of that function phi. Then what is the relation between the subdifferential of phi and the C subdifferential of phi? And the answer is here. Okay. What is the meaning? So you have so what is a C convex function? C convex functions are like this. You have family of these C supporting functions, each looking like this, right? And just it's easy. It's maybe it's good to consider the case when C is the distance square function. For example, C is x minus y squared over 2. Then you exactly have such a negative C function whose center is like in this case y. Okay. So you have all such functions, and you take a supremum, then you get some function phi, which is a supremum of this minus cxy by cy. Okay. Okay. Now, maybe let me draw it out a little bit here. Okay, let me give like 5 minutes overtime today. Okay. Right here, so you have your ID. Yeah, ID, and then you have your, let's say, this is point X. Okay. Okay. So you have this C convex function phi, which is semi-convex. Then what is the C subdifferential of phi at X? So phi at X, the C subdifferential of phi at X is nothing but the following. You consider all these supporting hyperplanes that supporting C function. So supporting C function that support the C function phi at X. Namely, that supporting function touches the graph of phi at X. You may have all different possible such functions. Let me draw it again. So you have phi here, and at that point, let's say X, you may have this supporting function, but you also may have some other supporting function, or you may have some other supporting function. Okay, so for the given X, you may have several supporting functions in the form of negative C xy. Okay, and And these y's are the members in the C subdifferential. Okay. And the claim is such y's is nothing but those y's. I mean, in this picture is very clear. Those y's where you take the derivative of C. So this function as a function of x. So this is derivative in x. Okay. This is as a function of x. You differentiate function. You differentiate this function in x variable. Okay. Then it means you consider the slope of this function. And then the meaning of this is that the slope of this supporting function belongs to the subdifferential of the original function, phi. I mean, because of this picture, it's obvious, right? When they touch this way, then this slope should be the slope of phi. Okay, that's the meaning of this relation. Okay, is that clear? Yes. Somebody nodded, but other people? James, is this clear? Okay, good. Yeah. So this picture is nothing but a translation of this writing. Yeah. Okay, then. Okay, I have 1 minute. So then, because of this, you can rather intuitively compute C subdifferentials of C convex functions. You just look at these, let's say, supporting functions, okay, and then just consider where these slopes are kind of matching. Then you just consider the corresponding y's. Okay, that's how you find C subdifferential. And with all these, you can, okay, so this is just exercise for inverse relation. You can actually translate or extend the statement of Brennier's theorem to the case for more general cost functions. Okay. And there, so everything can, this is almost the same as the previous Brennier's theorem, except that you have this relation between U and the mapping T. Okay, U is a C convex function coming as a solution to the dual problem, optimal solution coming as the optimal solution to the dual problem. And then the mapping, the relation between mapping T and the U is given by this. Okay. Now, just one comment. So Gangbo-Meccan theorem also says uniqueness of the transport plane T. I mean, existence of the transport. Okay, uniqueness of the transport plane T. Sorry, uniqueness of the transport plane pi bar, and then that transport plane pi bar be given as the optimal mapping. Okay, that's Gangbo-Meccan theorem tells, but that requires this additional condition for C. So this condition, whatever it is satisfied by the distance square cost function. Okay, but what is the feature is that the relation between this vector, the gradient vector, and the point y is 1-to-1. Okay, so what is this? So here, if you remember the previous picture I draw, given x, to compute a subdifferential, sorry, C subdifferential, you consider all those y's whose supporting C supporting function. Let's call this C supporting function, whatever it is. I mean, you know what it means. Touches the graph of the function at x. Okay, and then for the same slope here, you may possibly have different y's having the same slope as the gradient of C. Okay, if that happens, then given x, you may have different target points which violate the condition to be on mapping. Okay, so given X, you want only one result, Y. But if this happens, then given X, you may have different Ys, which you want to avoid. I mean, at least to have this nice theorem. So, so this is example is where this condition is violated. So given the slope, you have only one Y. That's what this condition means. Okay? If you have for the same slope, different kind of supporting functions with different Ys, then this condition is violated. But once you have such a condition, which can be satisfied by many many functions like this power function, p bigger than 1, and many others. Okay, many others. You have this Gangbo-Mekan theorem. Okay, sorry for over time.